Hi, everyone. It's my great pleasure to introduce Tatiana Brailovskaya from Princeton University, who will talk about universality and the matrix concentration inequalities. Please, Tatiana, the floor is yours. Thank you for coming.
All right. Yeah, thank you for the invitation. Yeah, I'll talk about some recent work we have in random matrix theory with my advisor, Ramon van Handel. I guess since this is a talk about random matrix theory, I'll first briefly talk a little about the different random matrix models that different kinds of researchers are potentially interested in studying, and I'll highlight sort of what it is that kind of we are trying to understand, what type of phenomena. So first of all, we have sort of classical random matrices, which have a lot of kind of homogeneity in their structure, like say IID entries. And for simplicity, we can assume that say they're mean 0 and have variance 1. I'll just call these like Wigner matrices, or maybe like some slightly different terms, and they're different like specialized classical ensembles, and these are really well understood. So in today's talk, I'll really kind of mostly focus on the edge of the spectrum of different types of random matrices, in particular just the matrix norm. So like one classical fact about Wigner matrices is that, if you rescale the square root of the dimension, the operator norm of such a matrix converges almost surely to the constant 2. This is just like one of the many things that are known. The point is just that these are like super well understood because of their significance in mathematical physics. But of course, these are very limited models. There are a lot of different other kinds of random matrices that people might be interested in understanding. Broadly, I'm going to call these structured random matrices. And again, just to like give you a few examples for like the flavor of the models that I would position in this class would be, say, sparse Wigner matrices. And these are basically the random matrices that have some fixed sparsity pattern, and then the non-zero entries are going to be IID. So like, one classical example for mathematical physics would be band matrices, but and those are very well studied, but then of course you can induce arbitrary patterns that fall outside of that and then are not nearly as well understood. Another example might be the series model, which kind of looks like as follows. So you take a linear combination of deterministic matrices AI and you multiply them by some IID scalars. So, HI, some IID scalars. And the AI are deterministic matrices. Another example that appears a lot, say, in statistics, and it's sort of a generalization of the types of random matrices that were studied like 100 years ago by Wishart, but the sample covariance matrix, which is a very important model. Here what we have is we have some matrix X with columns which are not necessarily identical, but say we assume they're independent. And we're interested in XX star, that's going to be the covariance matrix, which can also be written as like a sum of these XI stars. So again, these types of matrices show up a lot in all sorts of different applications. There are many more examples I can come up with. But the reason I kind of brought these 3 particular concrete instances up is that they're sort of actually a special case of the random matrix model that is really the subject of the work that I'm talking about today. So to be sort of precise, I'll define the independent sum model, which is kind of the model that Ramon and I are interested in. So the way we define this model is we consider a random matrix X, which is a sum of zi's, where zi's, first of all, they're independent, as hence the independent sum. So these are independent. their mean zero, their self-adjoint, and they have a bounded norm. So almost surely each CI has its spectral norm bounded by some parameter R. And we're also assuming they're square, so the dimension d by d. Okay, so let me briefly comment on these kind of assumptions. I mean, already what I wrote down is an extremely general model, but some of the properties I wrote down here are not really necessary. I'm just kind of putting them here for the sake of keeping things sort of clear and concise during the talk. So the first thing is that, here I put down mean zero, but this is really not necessary. This can be like arbitrary mean. So we can handle arbitrary means. Just, yeah, for simplicity, I put it here like this. Generally speaking, the self-adjointness, for some of our results, it's a necessary condition, but for the results involving the operator norm, this is not necessary. And this sort of boundedness condition is quite a strong condition. And in fact, this can also be relaxed. The point is mostly that we want the random variable that is the operator norm of each summand to be like reasonably well concentrated. And again, in this talk, I will just present results for the bounded ZI, but you can actually be weakened to the following. And we also have results that involve this other kind of quantity, which is essentially that the second moment of each CI has to be bounded. So it's actually like not a very strong condition. So the one condition here that is sort of really important and we really can't get around is like the independence. So I guess, yeah, this is, so we can't weaken this one. Yeah, it's possible that maybe you can somehow weaken it slightly, but perhaps not in a non-trivially meaningful way. So yeah, so that's kind of a really important part of the definition, but everything else is sort of there for convenience. And again, similar to the dimension thing is also, we can handle rectangular matrices. Okay, so now that we've sort of discussed the model, let's talk about like, how do we study an object like this? Of course, this is like extremely general, and a lot of random matrix theory is really focused on specialized models. So kind of how do we think about an object like this? So one sort of perhaps obvious idea is that, well, there's a very superficial similarity here to just like objects that we study in classical probability. Like when we look at, sums of independent random variables, we have all sorts of results that we learn when we first learn probability, like central limit theorem, over law of large numbers, like various concentration inequalities, like there are all sorts of effects like that. And that's really where a lot of the early inspiration was found on how to work with these objects. So the idea is kind of like try to adapt the proofs of scalar concentration inequalities to this matrix setting. So, and if that sounds a bit vague, I will give some examples shortly. So try to adapt proofs of scalar concentration inequalities to, I guess, the sum of CIs. And this, I mean, perhaps relatively naive idea has actually turned out to be very powerful, and that's how we end up with one kind of well-known result, such as the noncommutativity inequality. And this is, I mean, there's slightly different formulations, but I'll present the one that is for, I guess, the Gaussian series, which is not exactly the model that we're studying here, but it's similar enough, and it will kind of give you the flavor for I guess, the type of results that there are out there. So again, here we have this linear combination of some deterministic matrices, AI, which we assume are self-adjoint, and the GIs are IID standard Gaussians. And what is known in this setting is that the expectation of the operator norm is bound above up to universal constant by this parameter sigma x times square root log of the dimension. Okay. And the sigma parameter is kind of like a standard deviation parameter in the matrix context. Okay. Another example that actually applies to the independent sum that I defined here would be the matrix Bernstein. And yeah, maybe you don't remember these concentration inequalities off the top of your head, but the Gaussian inequality is like a classical result from also like 100 years ago about norms of sum of independent random variables. And similarly, like matrix Bernstein also has a scalar version. It's yeah, it's a well-known classical inequality. But so the matrix one, here's what this says. So we can bound the expectation of the operator norm, again, up to universal constant by the first term kind of similar to the non-commutative tension, plus this other second term, R of x, that depends on the R of x parameter. Okay, so if you've never seen these inequalities before, it's sort of, it can be a little bit puzzling how to make sense of them. Like, are these like some very trivial statements? Do they actually capture some non-trivial features of the spectral norm? So in order to kind of make sense of this, we'll just consider kind of a very simple example, which is the Wigner matrix, which I've mentioned before is quite well understood. So for the Wigner matrix, you can calculate the sigma parameter, and you will see that it's equal to square root of the dimension of that matrix. And now if you have a Gaussian Wigner matrix, you can try to bound its operator norm with the non-commutative tension. So in the Gaussian case, we get the expectation of the norm is bounded above to universal constant by square root d log d. And in the non-Gaussian case, by matrix Bernstein, we get that the operator norm is bounded above up to universal constant by d log d, or square root d log d, plus r log d. And here r can just say be the bound on the L infinity bound on the entries, say, of the Wigner matrix or something like that. So I guess, as we can see, maybe let me just state the correct result. So, or the correct result, since of course we know what the answer is in this case. Which I already mentioned at the beginning, but the correct sort of answer here is that the expectation of the norm of x should behave like 2 square root of d. Okay. So with all of this in mind, we can see that actually, even though both the non-commutative tension and the matrix Bernstein are quite general, at least when applied to this special case of the Wigner matrix, they sort of only miss this logarithmic factor that shouldn't be there. And again, depending on the type of maybe application that you have in mind, maybe this extra square root log of the dimension is not a big deal, but there also are, of course, situations where the log is quite significant, and you know, in fact, it would be nice to you know, find out when we can actually remove the log. And also, I think if we do have a theory of these very general matrix concentration inequalities, it would be nice to have it such that at the very least some of the classical examples are sort of captured correctly. Like, of course, we cannot hope for an inequality, say like the non-commutative that's going to be optimal for every single Gaussian random matrix, but it would be nice if it's at least optimal for, say, the Wigner case and a couple of other interesting canonical examples. So that sort of motivates, I guess, the work that I've been doing and some other people as well on sort of trying to remove this logarithmic term. And sort of
Tatiana, we had a question in the chat. The question was
yes.
if these inequalities have a parametric expression for an LP norm.
I'm not sure what you mean by parametric expression, but I mean,
Yanis,
here I'm stating.
Do you have?
You mean like
these are L infinity norm results, right?
Mm-hmm.
I was asking if there was if you could work these in an LP norm, and P would be the parameter.
Oh, I see. Well, we can have results for Schatten norms. I don't think we have results for arbitrary LP norms otherwise. Yeah, but perhaps some of the results can be extended to other norms. But yeah, we have. I guess yeah, maybe the answer is no. Yeah. Okay. So yeah, I guess the next thing I wanted to say is that sort of the premise of our work and is that somehow there's a very fundamental flaw in this kind of matrix concentration approach, which is that of course random matrices don't commute, and somehow trying to force them to commute loses a lot of information, and that's a kind of a core reason why these inequalities are not sharp. And like you can even pinpoint that in some of the proofs and really see how information is being thrown away for this sort of like forced commutativity. So that's sort of like the main problem. In some sense, yeah, like forcing the ZIs or the AIs to commute. Sort of creates suboptimal bounds. And so, yeah, I guess a lot of the recent work along these lines has been in the direction of trying to really take advantage of the fact that the ZIs or the AIs are kind of potentially highly non-commutative, and how do we use that to our advantage, and how do we get improved bounds, even just for like the usual most basic operator norm and not some other like fancy norm. So one such result that's been quite prominent in this direction is due to Alfonso Bandera, Ramon van Handel, and March Hardro. And here they prove something again for the Gaussian series, which again, not exactly the setting I'm working in, but like similar enough that a lot of the ideas turn out to be sort of relevant. So what these authors showed is that here you can bound the expected operator norm as follows. So okay, maybe have a new parameter here. So sigma here is the same as in the non-commutative inequality, and V is a parameter that is related to the norm of the covariance matrix of X. So basically, we take our matrix and I guess we can vectorize it, and then we look at the pairwise covariances of all those entries, and then we take the norm of that matrix, and that's how we end up with this parameter V. And if you kind of look carefully at the proofs, you can see that this is actually somehow the parameter that ends up controlling the degree of noncommutativity between these AIs. And somehow, like, if the parameter v is small, it means that the AIs are like highly noncommutative, whereas if v is like relatively large, then that means they kind of commute well. And perhaps just using the usual matrix consternation inequalities is sufficient, and you don't need to develop this whole fancy new theory that really tries to be a little bit more subtle. So again, and this parameter C here that I didn't say anything, this is just a universal constant. So again, just a few maybe comments to kind of unpack this result a little bit. So one thing is sort of, okay, the obvious question is how does this compare to the non-commutative Khinchin? Well, you can calculate and show that this theorem improves over non-commutative Khinchin as soon as there's a following relationship between v and sigma. So if you can show that v times log d to the 3/2 is less than sigma, then this new result is better. And in particular, again, it's maybe not exactly obvious from the way things are written down, but in a lot of the sort of interesting examples that we tried to apply these theory to, some condition like this will hold, and it will indeed be true that like v is much, much smaller than sigma. Another sort of simple kind of observation one can make is that if you plug in the Wigner matrix, you're going to get the correct result in a sense that, so this theorem correctly captures the Wigner case, meaning like if you plug it in, you do get something that's like the expectation of the operator norm is bounded above by 2 plus some smaller order terms times square root of the dimension. Okay, and when we were looking at the earlier examples, we not only couldn't get this square root d, we couldn't get rid of the log, but we also didn't have the right constants. So this is already a great improvement, but of course we're not, the authors of this paper that I mentioned here, worked really hard to get these results, and yeah, you can get much more interesting consequences than just recover some basic fact about Wigner matrices that you can prove in much more straightforward ways. And so to kind of maybe help ground ourselves and maybe convince you that this is something interesting and really powerful, I would like to mention maybe another Wigner matrix model that we'll also like revisit later and study it from the perspective of the new results that I would like to talk about today. So here, this is another sort of structured Wigner matrix model that is quite interesting for applications. Which I'll call the independent entry model. So basically what we have here, we have X that is a symmetric Wigner matrix with independent entries, as you might guess from the name. But the sort of interesting part comes in with in the variance, which is that we can allow the variances of the entries to kind of vary arbitrarily, and this way we can encode all sorts of like very interesting patterns and get very different behaviors. So for simplicity, again, we're just going to assume everything is centered, but we can have these like crazy variance patterns. And we encode it by these Bijs. Okay. So yeah, I guess maybe first we can, we can see what happens if you apply theorem 1 that I wrote down here to this independent entry model, because I think you get some pretty interesting results that way. So in order to do that, we need to calculate the model parameters. And again, I won't do the calculation, but I'll just tell you like what the answers are. So the parameter sigma, which is not very difficult to evaluate, is the maximum of these kind of L2 norms of the BIJs. And V can be shown to be like up to some constant equal to the maximum of the BIJs. So, okay, with this in mind, now if we apply theorem 1, we get the following. And this isn't like just directly plugging it in, you have to then massage the expression that you get a little bit with like times inequality, things like that. But essentially you get the following. So up to universal constant, you can bound the norm of this very general independent entry model by this maximum of the Bij norms plus another term. And as it turns out, two of the authors of this work that I'm mentioning here, Afonso and Ramon, have actually like studied the independent entry model itself quite extensively. As it turns out, that's already like something quite non-trivial. And what they found is that they actually tried to prove an inequality of the form that I wrote down here, where you have this, this first term is the same, and the second term is the same. Like it's this maximum of the Bij's times some log d to a power. And what they found is that sort of the correct answer is that you can prove an upper bound that looks exactly like this, except the 3/2 should be 1/2. And furthermore, you can even, if you make some homogeneity assumptions on the Bij's, like basically excluding situations where like you have, say, like one entry that's really large or some small number of entries that's really large, that's really dominating the matrix, this is also true up to a lower bound. But this is under some additional assumptions. And again, this is all in the Gaussian case, but still it is quite impressive because, just to get this result for the independent entry model, like the authors had to work really hard. And here we basically get it immediately from just like an application of a very general theorem that, applies to all Gaussian random matrices. And again, as you can see here, like this maximum of the Bij's times the log, that's sort of the smaller order term. And, in particular, the fact that here we have the wrong power of the log on the log it's maybe less consequential than when we have this extra log in the non-commutative condition. So this was all to say that kind of this new theory that was developed by Afonso, Ramon, and March is potentially quite powerful and actually contains some very deep insights on how to use non-commutativity of these random matrices that kind of can be represented as a sum. And we took a lot of inspiration from that work in now studying the independent sum case. And again, one sort of very natural question in the context of the independent sum, especially given that we have all these new amazing results for the Gaussian random matrix, is can we prove a sort of matrix central limit theorem that would allow us to relate these independent sums to certain Gaussian random matrices? So, and again, that's sort of our intuition, even if we just think very naively about scalar random variables. So, can we sort of prove a matrix CLT for the independent sum model? And again, I mean, such a result, of course, is itself interesting whether or not such a phenomenon occurs, but it's also quite useful because now, instead of having to bound, the norms of these complicated non-Gaussian models directly, we can just kind of plug things into the central limit theorem and use the bounds that have already been obtained in the Gaussian case, which is quite nice. So yeah, I guess as I've sort of already revealed, the answer to this question that I wrote down is yes. And kind of informally, what this matrix CLT states is that, again, under some assumptions, the spectrum of our general Random matrix X is close to spectrum of G, where G, as maybe is quite natural, is a random matrix that has the same mean and covariance structure as X. So okay, G is Gaussian. Okay. So now let me like state an actually concrete result, because this was all sort of hand wavy. And again, just in order to focus on the norm, I'll state our result for the spectral norm. Okay, so this is okay, so what we showed is that if you look at the difference between the operator norm of X, which is the independent sum, and the operator norm of G, which is this Gaussian matrix with the same mean and covariance, that difference can be bounded up to a universal constant by a bunch of these different terms. Again, we have the covariance, sort of noncommutativity parameter, V, and we have a bunch of other terms. Okay. This was kind of a long expression, but maybe now let's just take some time to make sense of it. So first of all, there's universality in the title of my talks. Maybe I would like to clarify what I mean by universality, because especially in the random matrix context, it has a very specific meaning, and I'm not using it that way. So by universality, I just mean when we have the following situation. The expectation of the norm of X can be shown to be roughly equal to the expectation of the norm of G. So we have some smaller order terms potentially, but they sort of become negligible in a particular limit. So now how do we actually devise conditions for such universality? Well, for this, we're going to use the following very nice fact that is known for Gaussian matrices. There's actually this very nice, simple lower bound. Can show that the operating norm of G is bounded below by the sigma parameter. And because of the way we chose G based on X, the sigma parameter for G is equal to the sigma parameter for X. And so now one way you can devise conditions for universality, basically you want to make sure that, you know, whatever this complicated stuff on the right-hand side is like asymptotically smaller than the expectation of G, which will necessarily happen if it's like asymptotically smaller than the sigma parameter. So particular universality occurs if this right-hand side is much, much smaller than sigma of X. And so now this is just a matter of doing some simple algebraic manipulations. And what we get is some conditions, some sufficient conditions for universality would be, so R of X is much, much smaller than sigma over log D squared. And the other condition is B is much, much smaller than sigma over square root log the dimension. Okay, so again, I claim that these are not very severe conditions, that a lot of interesting ensembles actually do satisfy this. And, in particular, we think of, R and V being kind of like the small parameters in a lot of the interesting examples. And one place to sort of see that is to revisit the independent entry model that I was talking about earlier. So for instance, if we try to apply this theorem to the independent entry case, we can see that universality is guaranteed when the following condition holds. So it's actually sufficient to just have R be much, much smaller than the following, the maximum of the Bij's over log D squared. So as we can see, this is not a unreasonable condition as long as not too many of the Bij's are not too small. Yeah, and as a sanity check, we can even plug in the Wigner case now, and we can see that sort of some very, very weak form of Wigner universality is also recovered. So, so in the Wigner case, it is known that, regardless of whether or not your entries are Gaussian or non-Gaussian, the spectral norm behavior will sort of be the same. So we expect the sort of universality that I wrote down here to apply. And in this case, the sufficient condition would be that R has to be much, much smaller than square root D log D squared, which will hold if, say, R is just an arbitrary constant, or even if you let R grow with dimension sufficiently slowly, this will necessarily hold. So some like weak Wigner universality, which again is sort of always good to have, given these well-known facts, so we can kind of recover them from our very complicated theory. I guess one more thing I would like to say in terms of the types of results that we have is that here I wrote down something for the operator norm, but this theorem is actually a corollary of a stronger statement, which says something about the Hausdorff distance between the spectrum of X and the spectrum of G. So it's just a little bit more complicated to write down, but it's a kind of an analogous statement. So we also show some universality for this statistic. Yeah, and I guess by universality, I mean like we prove an asymptotic estimate from which then you can deduce some form of universality. Another sort of silly remark is that we prove this sort of an analogous theorem to theorem 2 for moments, for Chapman norms, as I mentioned earlier. And so from that, you could try to recover, or you can recover the central limit theorem like the classical one, but that's definitely an unnecessarily complicated proof of that statement, but that's just like a fun little detail. So let me just maybe take the remaining time to talk very briefly about the proof. I'll just try to highlight sort of like the main ideas that we used. Unfortunately, I don't have enough time to go through a lot of the details, but hopefully the main idea will become clear. So the main sort of idea is to kind of pick up cleverly chosen spectral statistics and try to understand how they behave for X and for G. So bound expectation of X minus the expectation of F of G. And here, for F, I can't just plug in, say, the spectral norm, because it's not going to have sufficiently nice kind of properties to really be able to use any sort of analytic techniques that we would like to use. So the functions F need to be chosen sort of cleverly. In particular, sort of one nice function to work with would be like the moments of the random matrices. That one is like relatively easy to analyze, or it's easier than some of the other statistics, and it carries a lot of information about the spectrum. The main sort of statistic that we really wanted to analyze is the moment of the resolvent. So something like this for different values of Z. And this statistic is the one that sort of gives you the spectral universality. The moments aren't quite strong enough to capture that. So, okay, keeping this in mind, how do we now bound this kind of difference? Say we've chosen our spectral statistic that we want to work with. So the idea is to use interpolation. Which again is a very, I think, fairly commonly used idea in universality work. So we set up our interpolation as follows. So we will isolate the mean. Again, here I've just worked with the zero mean case, but if you don't have a zero mean, you want to isolate it like this. And basically the idea is that, at X equals 0, you have the Gaussian matrix, and then you kind of smoothly transform it into our actual matrix X. And sort of a nice feature of this interpolation that, the mean stays constant as you kind of interpolate, you transform G into X, but also the covariance structure remains unchanged. So the entry covariance doesn't change. Okay, so now that we've set up our interpolation, we're going to do something very kind of simple. We'll apply the fundamental theorem of calculus to write the difference as an integral. Okay, and so now maybe it doesn't necessarily look like it's a more tractable problem, but we've reduced the problem of studying this difference to studying this like derivative. So our goal is to now understand how this derivative behaves. And somehow it turns out that studying this derivative is much nicer. It allows us to use all sorts of identities, and I guess sort of intuitively, one would think that, the jump from f of x to f of g should be quite large. However, if you have this very nice smooth interpolation, the change in the function f along the trajectory of the interpolation should not be like too large. And so presumably if you can control how f changes along this trajectory, you can control like the whole difference. Again, this is sort of hand wavy, but that's the general idea. So now what actual tools do we use in order to to bound this derivative and to kind of do anything meaningful with it? So we use this technique called cumulant expansion, which I guess you combine this idea of interpolation and you use cumulants, which essentially allow you to perform something like Gaussian integration by parts, but for arbitrary random variables. And this is a technique that kind of has been, I think, used quite a bit in random matrix theory, but maybe in slightly more classical situations. So this kind of interpolation, cumulant expansion. And this is a technique that was initially kind of developed by Latova and Pasteur, and they used it to prove universality of linear spectral statistics of Wigner matrices. And yeah, so I guess you can see our work as sort of like an extension of those ideas, but to this more general setting. And then, so actually we use these really nice techniques from, I guess, more classical random matrix theory. We get these very long, complicated expressions that involve a lot of matrix products. And then we simplify all those matrix products using something called like trace inequalities. These are basically just holder type inequalities, just like they look more, they're just like a bit more general and yeah, I guess look a tiny bit more complicated, but that's sort of the main other tool. And so I guess we kind of think of this like first part, the interpolation, the cumulative expansion, as kind of being like the classical random matrix theory toolkit. And then we think of trace inequalities as kind of being more operator theoretic. And somehow it's this combination of these two somewhat different kind of areas of mathematics is what really allows us to then obtain the kind of very general results that we have. Again, hopefully this was at least somewhat clear to some of you, this part about the proof. I'm happy to answer more questions about that or any other part of the talk. And I think that's all I have. So thank you for your attention.